In organic chemistry, nucleophilic substitution is a fundamental reaction where an electron-rich species, called a nucleophile, replaces a leaving group on a carbon atom. Understanding how this happens allows us to predict the products of countless chemical syntheses. There are two primary pathways for this reaction, SN1 and SN2. The S stands for substitution, N for nucleophilic, and the number represents the molecularity of the rate-determining step. Let's dive into the mechanics of each process. SN2 is a bimolecular process, meaning two molecules are involved in the single, concerted step. The nucleophile must attack the central carbon from the side exactly opposite to the leaving group, a maneuver known as a backside attack. During the reaction, a high-energy transition state forms where the carbon is momentarily bonded to both the nucleophile and the leaving group. This state is unstable and leads immediately to the expulsion of the leaving group and bond formation. Because the nucleophile attacks from the back, the spatial arrangement of the other substituents is pushed forward. This results in a complete inversion of configuration at the carbon center, much like an umbrella blowing inside out during a storm. Steric hindrance is the enemy of SN2. As we add bulky groups to the carbon, it becomes harder for the nucleophile to reach the center. Consequently, primary carbons react quickly, while tertiary carbons are too crowded for SN2 to occur. In contrast, SN1 is a two-step unimolecular process. The first and slowest step is the spontaneous loss of the leaving group. This creates a positively charged intermediate known as a carbocation, which is the hallmark of the SN1 pathway. The carbocation intermediate is trigonal planar. This flat geometry is crucial because it leaves the carbon open to attack from either the top or the bottom side in the subsequent step of the reaction. In the second step, the nucleophile attacks the carbocation. Since the intermediate is flat, there is an equal probability of attack from either side. This leads to a mixture of different spatial arrangements in the final product. Because the attack occurs from both sides, SN1 reactions typically result in racemization. If you start with a single enantiomer, you end up with a mixture of both, effectively cancelling out any optical activity in the sample. SN1 reactions favor substrates that can form stable carbocations. Tertiary carbons are the most stable due to electron-donating effects from surrounding groups. Therefore, tertiary substrates are the ideal candidates for the SN1 mechanism. Comparing energy profiles, SN2 shows a single energy barrier. SN1 shows two barriers with a local minimum in the middle representing the carbocation intermediate. The highest peak in SN1 represents the slow, rate-determining step. Let's look at an example. Methyl iodide reacting with sodium hydroxide follows an SN2 path. Since methyl is unhindered and hydroxide is a strong nucleophile, they collide in one step. Doubling either reactant concentration will double the reaction rate. Now consider tert-butyl chloride in water. This is an SN1 process. The rate depends only on the concentration of the alkyl halide. Adding more water won't speed up the reaction because the slow step is the chloride leaving. Solvents also play a role. Polar aprotic solvents favor SN2 by not caging the nucleophile. Polar protic solvents, like water, stabilize the carbocation and leaving group, which significantly speeds up the SN1 pathway. To summarize, SN2 is a one-step backside attack favoring primary carbons and resulting in inversion. SN1 is a two-step process through a carbocation, favoring tertiary carbons and resulting in a racemic mixture of products. Quick question: which mechanism is favored for a secondary alkyl halide in a polar aprotic solvent with a strong nucleophile? The answer is SN2. Strong nucleophiles and aprotic solvents push secondary substrates toward the bimolecular pathway. Generated by Vision Solve AI.